Oh, hey there, guys. I didn't notice you there. So, welcome to this lovely little area of science, okay? So, this is the messed up ballistic pendulum we made. Before we continue, I'd like to remind everyone that safety always comes third.
Third, what happened to second and first?
Well, you see, weird person that I don't really know. First is knowing the right saw to use. Because guess what? It's really fun when they make funny sounds.
What the hell does saw sounds have to do with anything?
Because saw sounds are cool. And why not? Also, second rule to the lab is, if you can imagine it, you can make it out of wood.
What the hell do you mean you can make it out of wood?
Well, what I mean by you can make it out of wood is, even if it's something as complex as simulating a ballistic pendulum, you can make it out of wood.
Well then. Okay.
Thank you for leaving. Now, where were we? The way that this works is we are using gravity as our friend right now. And what happens here is we take this metal ball bearing, average, you drop it from here. Now, I've had a couple of problems with this because this was originally a magnet. Now, of course, everyone's going, well, Alex, it's a magnet. It'll add magnetic potential energy. And I'm like, yes! I know! That's why I changed it. But because I changed it, it's really awful to work with. As you can see, it's kind of a little metal cage made out of copper wire so that it's non-magnetic. Now, the thing that's so annoying about this is that it takes very precise alignment when you start over here to make sure that it actually gets caught. Otherwise, I don't know if it'll work this time or not. It will just kind of, not go in. Now, the weird thing about this experiment is that when I first started making it, I got my dad to help me, because of course, woodworking, I'm just a little skinny guy, and I don't know much about woodworking. So we built this entire thing, and if you look over here, you'll see that there are so many lines. We looked at this and went, well, since it's energy transfer, it'll just go all the way back up to about the same height, if not a little bit less. Now, the problem with this is the fact that because of the collision that happens here, it doesn't keep its energy. Now, why wouldn't that work, you might ask me? Well, it's because it's an inelastic collision. Now, what's so special about inelastic collision? Inelastic collisions, only momentum is conserved, not the energy. Now, how do we work this out? How do we know what height it's supposed to go, or what speed it'll be going? Well, we figured this out by rearranging formulas and adding them together. I'll probably show it somewhere on the screen. Now, with this formula that's on the screen right here somewhere, just for simplicity, depending on the height, we will know what velocity it should have been going. Now, because we're using tracker, we'll be able to know how accurately this formula can find the speed, because we will know the speed just before it goes into this. Now, also using the pretty bad camera that I'm using right now, it can't see many frames. So another problem we had while doing this was the fact that you'd see the ball for this distance, this distance, this distance, and suddenly it'd be inside the net. Now, another problem we had was we thought, well, the lighting is kind of, a little bit bright up here, and there's no real way to reduce glare. And not only that, but if you were to move this curtain, which I'll see if I can do, you'll notice that there's a lot of stuff back there. And when the marble was originally rolling, it'd be like, oh, well, there's stuff back there. What do I do with the stuff back there? And we'd go, well, damn it, just follow the marble. And it'd be like, but that's no longer the marble. And we'd go, yes, it is. And it'd just go, no, it is. So now we're faced with an entire new obstacle of having to hand track every single point. Now, even though we're tracking it by hand, bit by bit, it's still not as accurate as we'd like it to be. Because guess what? First off, we can't properly find where it is. And second off, as soon as it enters this goes into a blur. And because of the fact that it's half see-through, it gets even harder to. So who knows? We may have made errors there. Now, another error is the fact that we lose so much energy on this ramp alone because of the fact that there's so much friction. And this friction is already reducing it. So when we were originally calculating it so that we'd figure out how fast it would go here, it wasn't going half as fast as we thought it would. Because of the fact that it wasn't going as fast as we thought it would be, it didn't go half as high. Now this was another problem that we pointed out. So as the ball's going down, it gets caught in this, right? Now, because of the fact that it needs to be so close to the board, it was even making contact with the board and rubbing along. Now, if you were to zoom in right here, you'd even see the fact that there is a clear path where dust has been removed. And guess what it follows? Right here, the side of the net. Now, because of the fact that it was rubbing against the board so much, we lose so much speed, which means it doesn't go half as high as it should be. When going through Tracker and doing all my calculations later, I realized that for the height I was getting, it could have been going a lot slower. Which means that technically speaking, I would be able to calculate how much energy / speed was lost just due to the fact that, it's rubbing against the side. Formulate words, formulate words, formulate words.